Okay, so in this video we are going to talk about function value trends that we evaluate on the x-axis. So in general we're saying here that we have trends in function values that are being determined by the x values we're plugging into the function, and we want to determine what x values are causing these trends to occur. And when we do this, we evaluate trends of the function values by determining the x values in which they occur from left to right. Examples of this would be increasing and decreasing, where what x values make our function values increase, what x values make our function values decrease, and positive and negative, what x values make our function values positive and what x values make our function values negative. And when we're asked to evaluate these things, we're always going to be looking at the intervals of the x-axis that cause these function value trends. So right here, one way we can think about this is how long does the function follow the trend? And in general, what we're going to say is, these things are pretty easy to evaluate if we look at them graphically. Where function values are positive, we're obviously above the x-axis. Where they're negative, we're below. Where our function values are increasing, we're seeing our function go up. Where function values are decreasing, we're seeing our function go down. But we want to think about where these things are happening on the x-axis in terms of determining where they are. So right here, we are given a graph of a function to our left, and we want to determine where this graph, which we're calling the function f, is increasing, where it is constant, and where it is decreasing. Now, constancy is not something we're going to see a whole lot. Mostly we're going to be looking at where function values are increasing and decreasing, but it's worth it to take a second and evaluate this and make sure we understand what this means. So when we're talking about a function increasing, we're talking about what x values make our function go up. When we're talking about a function being constant, we're talking about what x values make our function value one constant number. And when we're talking about decreasing, we're obviously looking at what x values make our function values go down. So right here, looking at our graph, we can immediately say that we're seeing our function go up on the x-axis interval from 3 to positive infinity. Right? So this would be where our function is going up, and we're saying that the x values from 3 to positive infinity make our function increase. So writing this in interval notation, we would say that our function is increasing from 3 to positive infinity. We would say that the x values that make our function constant are going to be the x values from negative 3 to positive 3. And we're seeing our function have the constant value of 3 on that interval. So right here, where's our function constant? On the x-axis interval from negative 3 to positive 3. Finally, right here, we're seeing our function decrease right here, and that's happening on the x-axis interval from negative infinity to negative 3. And so right here we would say that the x values that make our function values decrease or go down are from negative infinity to negative 3. So in general, I think it's pretty easy to evaluate increasing and decreasing on the graph. And really what we're looking at is to just sort of make sure that we understand that when we're asked to determine increasing and decreasing, we want to know that we're talking about what x values make our function increase and what x values make our function decrease. Another way we can think about this is where are we increasing or decreasing on the domain. So basically, if we look at this function as being sort of having a domain of negative infinity to positive infinity, which it certainly seems like it does. Looks like we're covering all of the x-axis here. We're getting every x value in an ordered pair. We'd be basically looking at breaking up the domain into the intervals where we are decreasing, increasing of course, and constant. So right here, constancy, as we've already said, is not a trend that we normally see. in order for us to be constant, we have to be looking at a series of x values that give us the same y value. And generally, one order pair is not going to be considered a place where we're constant, right? So if we're looking at this curve, we can see here that we've got a max at 0, 6, and we've got a min down here at 4, -6. There's no place where this function is constant, right? It's either going up, it's hit a max, it's going down, it's at a min, or it's going up, right? So what I want you guys to do is to determine the intervals where our function is increasing and decreasing. And we're going to pause the video for a second and give you guys a chance to do that. For this one, and for a lot of functions that we're going to see, we can say that it's constant nowhere. So we would say there are no intervals where we're constant. Okay, so right here we'll go ahead and pause the video and give you guys a shot at this one. All right, so again, when we're talking about increasing and decreasing, we're talking about what x values, what interval of x values will make our function values go up as increasing, and what x values or intervals of x values will make our function values go down. And clearly we can see that we are increasing on the interval from -infinity to 0 and from 4 to +infinity. So right here we would write this with interval notation as increasing on the intervals from -infinity to 0, union with 4 to +infinity. And we can see our function decrease between the max and the min. And right here, that would mean that we are decreasing on the x-axis interval from 0 to 4. Okay, so we're going to try one that's a little more challenging now. Here we have a function that is basically broken by two vertical asymptotes. And right here, if we look at the denominator, take that equal sign out. If we look at the denominator here, we can factor it and determine what those vertical asymptotes are, what those zeros in the denominator are. So right here we've got the factors of, looks like, x plus 1 and x minus 7 as being the factors of that quadratic in the denominator. We set them equal to 0, and we can see that our vertical asymptotes happen at x equals -1 and x equals +7, which is basically confirmed on our graph. Those vertical asymptotes correspond to the holes in the domain. And so really, if we're looking at this graphically, we can say our domain is going to be -infinity to -1, union with -1 to 7, union with 7 to +infinity. Now, this is a problem where it's helpful to really say, where on the domain are we increasing and decreasing? Again, we're constant nowhere here because you pretty much have to attain one function value over an interval of the x-axis, and we're clearly not seeing that anywhere here, even though our function is flattening out to the horizontal asymptote of y equals 1, which we can see. But it's never getting completely flat because those y values are just getting closer and closer to 1. So we're not seeing any constants. So right here, what I want you guys to do is to go ahead and try to determine the intervals where our function is increasing and decreasing. The one thing I'm going to say right here, and we'll sort of give you this one, is we can, if we type this into the calculator, we can determine a local max at the ordered pair 3, and then right here we would say 0.25. So right here, we want to go ahead and determine where this function is increasing and decreasing. And again, we want to think that's where is it increasing and decreasing on the domain. So we're looking to break up these intervals into intervals of increasing and decreasing. So we'll pause the video here and give you guys a shot at this one. All right, so taking a look at this one, as we look at our function, we can see that it's increasing on this first interval of its domain. So we're increasing up into that vertical asymptote. Then after the vertical asymptote, we continue to increase to the max that we're seeing happen at 3. So again, these are x-axis intervals where we're increasing and decreasing. And again, we can say basically that we're increasing on the interval of the domain from -infinity to -1, where we see that break in the domain, and then from -1 to the x value where we see that max 3, right? Next, we can see that after we hit that local max, we're decreasing, we're going down. And right here, we go down into that second vertical asymptote. And then after that second vertical asymptote at 7, we continue to decrease into that horizontal asymptote. And so we'd say that we are decreasing on the second interval of the domain from 3 to 7, union with 7 to 3. So again, what you want to remember here is that we're talking about x-axis intervals. So really what we can think is we're breaking the domain up into intervals of increasing and decreasing. Now you'll definitely get more practice with problems like this in class tomorrow. We can also ask questions like, where is this function positive or negative? We'll really get to these kinds of questions more at the end of chapter 2. So we're going to hold off on this stuff for now. It's just an example of different trends that we can identify on the x-axis for function values. So right here what we're going to do is we're going to move on and talk about some other characteristics of function values. We're going to look at symmetry. So there are two types of symmetry we're going to look at. Symmetry with respect to the y-axis basically means that every ordered pair we have on one side of the y-axis is reflected across the y-axis onto the other side. So right here, if I have an ordered pair, right, that I might say is, let's say, A, and then the function value at A, that ordered pair is reflected across the y-axis such that we have the corresponding x value giving us the same function value. So right here we would say this would be negative a and f of negative a, which is also f of a, right? We'll erase that because really we're plugging in negative a there. So right here this is negative a and f of negative a. And what we can see is that f of a and f of negative a are actually the same y value, right? So one of the ways we can determine symmetry with respect to the y-axis is by saying if we plug in a generic negative x, will we get the function back? Because essentially what that's going to do is say that plugging in any negative number is going to be the same as plugging in the corresponding positive number. Now right here, this function is x squared, right? And when we plug in a negative x into a square, a negative times a negative is going to give us a positive. So we actually can say that negative x squared is the same as positive x squared, and that right here our x squared is symmetric with respect to the y-axis. Functions that are symmetric with respect to the y-axis we say are even functions. The second kind of symmetry we're going to look at is symmetry with respect to the origin. Basically what we're talking about here are functions that have ordered pairs reflected across the origin, diagonally, into that diagonal quadrant. So right here, if I've got my same ordered pair, let's say a comma f of a, or it's not the same ordered pair, but it's an ordered pair where we're plugging in that x value of a and getting out the y value f of a. Right here, basically what I'm saying is if I reflect this, if this point is reflected across the origin, to the corresponding point in the diagonal quadrant, if we plugged it in the first quadrant, then the diagonal quadrant would be the third quadrant, we would have negative a right here being negative a and then f of negative a. But right here, f of negative a is really the negative of the y value. So really what we're talking about is our ordered pair is negative a and then the negative of that y value for f of a, so negative f of a. And this is what we're going to use to determine odd functions, or functions that are symmetric with respect to the origin. So basically right here, if we're saying we're symmetric with respect to the origin, then plugging in that negative x value, right, is going to make the function negative. The example that we're seeing here for our odd function is the cube. And right here, when I plug a negative x into the cube, I get the negative of the cube. We'll look at these a little bit more moving forward. We may look at some of these that are a little bit more intricate. In general, what we want to think here is you should definitely be able to identify these things graphically. Typing a function into your calculator, you'll be able to see if it's symmetric with respect to the y-axis. just by looking at it, or does it look like we're symmetric? That's the first test. And then to show that it's symmetric with respect to the y-axis, we want to be able to show that this is true. Plugging in a negative x is going to be the same as plugging in a positive x. Right here, with our odd function, if it's tough to see if it looks odd, one of the things you can do is type the equation into the calculator, take a look at the graph, and if you turn it upside down and get the same picture, then it's a good indication that it's odd. But the proof is going to be, if I plug in a negative x, does it make the function negative, right? Does it make the function value itself negative? So right here, there's our even and odd functions. We're going to talk about one more thing, and then we're going to wrap up this video. The last thing I want to talk about is end behavior. End behavior is basically what's happening to the function values, the y values of the function, as x values go out to positive infinity and negative infinity. So as we continue to plug in x values going out to positive infinity, where are the y values in our ordered pairs going, right? Which are the function values. And right here in general, what we can say is that we use limit notation to determine this. So limit notation tells you where the x values are going, right? As x goes out to negative infinity, as x goes out to positive infinity. And it asks you what's happening to f of x, or the y values. Now in general right here, we can look at this parabola and say what's happening to the ends of this parabola as we plug in x values going out to positive infinity and negative infinity. As x goes out to positive infinity, we can clearly see that our parabola, this arm of the parabola, is going to go up to positive infinity. So we can say that the y values of the function, or the function values, are going up to positive infinity. Similarly, right here, if x goes out to negative infinity, we can say, as x goes out to negative infinity, we can say that our function values are again going up to positive infinity, right? So the y values in the ordered pairs are going up to positive infinity in both cases. Now, erasing all this stuff, we can determine this graphically, but we know this is a parabola. So, I mean, that's really how we can tell graphically what's happening. But in general, if we're dealing with polynomials, there's one way we can always determine what the end behavior is going to be. With regards to polynomials, what we can say is the end behavior always is determined by the highest powered term. And what we mean is that as x values get really, really large that we're plugging in, this highest powered term is going to be so much larger than the rest of the terms that these guys aren't even going to matter, right? This guy is going to be so large, he's basically going to determine where the y values of the function are going to go. So basically right here what I can do is take out x squared and say, what happens as I plug in x values going out to negative infinity? Well, if I plug negative numbers into a square, right, as I go out to, as those negative numbers get larger and larger, I'm basically just going to get positive values, right? So right here I can see that my function is going to positive infinity. As I plug in positive values into the square, going out to positive infinity, I get positive values going up to positive infinity, and I can say that my end behavior is determined by that highest powered term. So right here, we've got another end behavior problem where I'm asking you to determine the end behavior of this cubic right here, this third degree polynomial. And what I want you to do is determine in the way that we talked about it up here with regards to looking at that highest power term, right? So basically, we want to take the highest power term out and think about what happens when I plug in numbers going out to negative infinity, right? If I square negative numbers, I get positive numbers. And what happens when I plug in numbers going out to positive infinity? Squaring positive numbers also gives me positive numbers. And that's going to be what determines the end behavior for a polynomial. Now, after you do that, check the graph, right? See if it works out. So right here, we're going to pause the video, and we'll give you guys a shot with this one. All right, guys, so looking at this one, the highest powered term is that 4x cubed. So I'm literally taking that 4x cubed out of the equation. And I want to think about what happens when I plug in negative numbers into that 4x cubed. If I cube negative numbers, I get negative numbers, right? Multiplying those negative numbers by 4 they're still negative. So right here I can say as x goes out to negative infinity, that highest power term is giving me negative numbers, which means my end behavior is going to go to negative infinity. I'm going to get y values going down to negative infinity. When we plug in positive numbers into that 4x cubed, we're basically cubing positive numbers, which give us positive numbers, and multiplying those positive numbers by 4, which also is going to give us positive numbers. So we can say that as x values go out to positive infinity, we're seeing our function values, the y values of our function, go up to positive infinity as well. If we look at our graph right here, we can see that reflected in what we're seeing. X values, when we leave our graph with x values going out to positive infinity, we're basically seeing the y values of our function go up to positive infinity, and similarly, when we go out to negative infinity, we're seeing those y values go down to negative infinity as well. We'll get some more practice with this, and we'll look at it some more in class. And for right now, this is the end of the video, and I'll see you guys tomorrow.